Hello, everybody. Welcome to the August 2018 prelim video for problem 4. Some of you have requested this problem, and I think it's because there's a couple of tricky calculations here. Otherwise, it's a fairly straightforward problem. So in problem 4 from August 2018, we have a random sample x1, x2 out through xn. They are IID, normal, with mean theta and variance 1. And so we're using a slightly different notation. We're not using our mu, but that's okay. We can deal with this. Now in part A, we are asked to find the best unbiased estimator of theta squared. Actually, we're given the best unbiased estimator. So we want to show that the best unbiased estimator of theta squared is equal to x bar squared minus 1 over n. At first, it might not seem clear what is being asked here because it's not using the sort of standard wording. The best unbiased estimator, my guess is that this is the UMVU, the Uniformly Minimum Variance Unbiased Estimator. If you were in this exam, you could try asking the proctor. They may or may not clarify that for you. And if they don't, I would assume it's the UMVU, and I would write that. So I would write, I am going to find the UMVU, just so people can follow what you're trying to do, and then figure out whether or not you did that right. So to find an UMVU, we're going to use the Lehmann-Scheffé theorem, which has 2 steps. The first step is to find a complete and sufficient statistic for this model. And that is often done using the exponential family factorization. So we need to look at the PDF here. Now this holds for all x between minus infinity and infinity, so there's no indicator here. And now I want to write down the joint PDF. Because these are IID, I do get to multiply the original PDF. There's only one of them, but I go plugging in x1, x2 out through xn. And I'm just going to go straight for the punchline here rather than write that out. I'm going to get this n times, and that's like a 2 pi to the 1/2 in a denominator. You don't have to do this, but I like to write this as 2 pi to the negative 1/2 to the n, which is going to be to the negative n over 2. And I think I'm going to go ahead and write the e as an exp because the exponent is getting kind of chonky. And this is going to be 1/2 the sum as I goes from 1 to n of xi minus theta squared. So for one parameter exponential family factorization, we're looking for some sort of function of the parameter only that I'm going to call a of theta, and then a function of the data only that I'm going to call b of x, and then e of some function of the parameter only that I'm going to call c of theta, and the data only that I'm going to call d of x. And if we can get it in this form, then the d of x part here is going to be our complete and sufficient statistic. So to that end, I'm going to square this and run the sum through. And I do have to distribute that 1/2 across, and I am going to go ahead and start pulling things out into that a of theta, b of x, etc. form. So the 2 pi to the minus n over 2 is just going to sit here, and I'm looking for pure theta stuff. So that's going to come from this third term. That's going to be e to the minus n over 2 theta squared. And now I'm looking for pure x stuff, and that is going to come from this first guy. So this is going to be e to the minus 1/2 sum of the xi squared. And then finally, I'm going to get this times this, and that's where my x and theta stuff are kind of mixed together. So this is going to be e. Now the minus 1/2 and the minus 2 are going to cancel. I'm left with theta and the sum of the x's. And we have it in the one parameter exponential family form. In this case, this is my a of theta. that 2 pi part could be part of the b function as well, or instead, but I'm going to say that this is b of x, and then this theta alone is c of theta, and then this is d of x. And I'm kind of mixing up my lowercase and capital looking things here. But in the end, you want to state your statistic as a random variable with capital letters. So I would say by one parameter exponential family. I don't know why I always put quotes on that. You don't need quotes. I guess I'm trying to emphasize this is what you should say at this point. The statistic S, which is defined to be d of the capital X's, which is the sum as I goes from 1 to n of the xi, is complete and sufficient for the model. Okay, so that's part 1 of the Lehmann-Scheffé theorem for finding the MVU. We first want to identify a complete and sufficient statistic, and we've done that. So what we're trying to estimate here, what I'm going to call the target, is theta squared. So usually at this point, I would look at the expected value of this, and then maybe divide it by n and turn it into an x bar and the expected value of that. And that would have expectation theta. So then I would try maybe squaring this over n and seeing what we get there. That's not going to be theta squared, but maybe something you can adjust. But all of that is way too much work here because you're given the outcome. We want to show that the sample mean squared minus 1 over n is the MVU for theta squared. Now this is 1 over n s squared. So this thing as a whole is a function of the complete and sufficient statistic. And if we get theta squared out of this expectation, we are done. I'm going to run the expectation through. And then for the constant, I just get 1 over n. And then anytime I want to find the expected value of something squared, I like to unravel the variance, because the variance of something is the expected value of that thing squared minus the expected value of that thing all squared. So we can unravel that and write this expectation as the variance plus the expected value of x bar all squared, and then we just have that minus 1 over n hanging out over there. Now the variance for x bar is always the original variance, sigma squared over n. In this problem, sigma squared is 1, so if you want to go ahead and write that right there, that's fine. And the expected value for the sample mean x bar is the same as the expected value for any one of the random variables. In this case, it is theta. And I'm going to go ahead and put my 1 in for sigma squared. And we get nice cancellation. And we get what we were trying to find the best unbiased estimator or MVU for. So you can conclude this by saying, by the Lehmann-Scheffé theorem, x bar squared minus 1 over n is the MVU, the uniformly minimum variance unbiased estimator for theta squared. And we are done with part A. Part B is, I think, the tricky part that if you asked this question, this is maybe where you had some trouble. And that is in finding the variance of this MVU, x bar squared minus 1 over n. You're given some hints about the chi-squared distribution. You may recall that a normal 0, 1 squared has a chi-squared 1 distribution, but we're not dealing with a normal 0, 1 here. So I think we're going to have to adjust this a little bit. Also, you may not use the chi-squared at all. So that's the kind of curse of getting a hint. On one hand, it might make things easier for you. On the other hand, it might make you doubt yourself if you didn't use the hint. The first thing I'm going to do here is get rid of the 1 over n, because adding or subtracting a constant from a random quantity is not going to affect the spread. You're just going to move the points of the distribution, in this case, down on the number line by a distance of 1 over n. And now, as I was saying, I think I'd like to see a normal 0, 1, either to use the hint or not to use the hint, because it's still easier to work with than this random variable. So we have x bar is normal, and its mean is the same as the original mean, and its variance is the original variance, which is 1 over n. And this means that if we define a random variable z to be x bar minus theta over the standard deviation 1 over the square root of n, I'm going to rewrite this, put the square root on the top here. This has a normal 0, 1 distribution. And if you square that z, it has a chi-squared 1. So I am going to finish this variance calculation in 2 ways. One will be using the chi-squared distribution, and one will be not using it. So I really care about the variance of x bar squared. So let me solve for x bar in terms of the z. X bar is z over the square root of n plus theta. So x bar squared is, of course, that entire quantity squared. So what we want to find is the variance of x bar squared. And this is the variance of z over the square root of n plus theta, all squared. Your first thought here might be to write this out as an expected value of this z over the square root of n plus theta squared squared, so to the fourth, minus the expected value of z over the square root of n plus theta squared, and then a squared on the outside. And that will work, but I really don't want to take the fourth power of this thing, so I'm not going to do this. What I'm going to do is square it out, because I'd rather square something than take it to the fourth power. So squaring this expression out, I get the variance of z squared over n plus 2 theta plus 2 theta over the square root of n times z plus theta squared. And now I do have something random plus a constant, and the constant will not affect the variance. So this is the same thing as the variance of just the first 2 terms. So some of you might want to write this as the variance of the first term plus the variance of the second term. But that is only true that you can distribute a variance across a sum that way if you have 2 independent terms. So you would need this to be independent of this, and that's not the case here. One of them involves z and the other involves z squared. And we've seen weirder things happen. We've seen things in MathStat that look like they're not going to be independent, and they end up being independent. So maybe that happens here, but I certainly wouldn't assume that. So what am I going to do? I think now I am going to write this out with the expectation version of this. This is the expected value of z squared over n plus 2 theta over the square root of n z. I'm making a lot of decisions as we go, and you may not make the same decisions, but you'll end up getting there. It's just kind of a bit of work writing this one out. Let me go ahead and take, I am going to square this out, but at least I'm not taking a fourth power of anything. You will, or see fourth powers of things. But one thing I want to note over here is this expectation will distribute, and that second term has expectation 0, because if you take its expectation, the coefficient will come outside, and the expected value of a normal 0, 1 is 0. So this expectation will give us 0. That notation is maybe not so great. I'm not saying this is 0. I'm saying the expected value of that is 0. Okay, so now I am going to square this out. I am going to end up with a z to the 4th. I'm not afraid of that, but I just didn't want to have to take a 4th power of that original term. This is the expected value of z to the 4th over n squared plus 2 times 2 theta over blah, blah, blah. So I'm going to get 4 theta over n to the 3/2 and z cubed. And then finally, I'm going to get 4 theta squared over n z squared. And then over here, I've got the expected value of z squared over n, and that whole thing is squared. I get to run the expectation through being a nice linear operator. And let's take care of this cube term first. The standard normal distribution, or the standard normal random variable z, is symmetric about 0. And that's why its expectation is 0. It has the same probability mass on both sides. And I think you can pretty easily convince yourself that the same thing is going to happen with z cubed. The expected value there is going to be 0. And in fact, the expected value of a standard normal to any odd power is going to be 0 because, all the points between, say, 1/2 and 3/2 are going to map to 1/4 and 9/4. And all the points from negative 3/2 to negative 1/4 are going to map to the same negative 9/4 to negative 1/4. And you can probably convince yourself of that. But I am going to find the expected value of z to the 4th. And if you're not convinced about the cube term, you can do that one in the same way I'm about to do the 4th term. So I'm going to run the expectation through, and this one has expectation 0. Any odd power of a standard normal does. While I'm at it, I'm going to pull out that 1 over n squared. Over here, I'm going to pull out the 1 over n, which will end up getting squared when it comes out of those parentheses. So the expected value of z squared is not bad. We have our standard trick of rewriting the variance formula. And z is normal 0, 1. So that expectation is 1 for both of these terms. The z to the 4th. I have 2 ways I could approach this. So it seems like a very high power, and I don't want to put z to the 4th in front of the standard normal PDF and try to integrate. So one thing I can do is use moment generating functions. And this is the longer way to do this, but I did say I would do it 2 ways. So the moment generating function of the standard normal is e. So in general, for a general normal with mean mu and variance sigma squared, it's e to the mu t plus 1/2 sigma squared t squared. But in our case, the mu is 0 and the sigma squared is 1. So I just get e to the 1/2 t squared. Yeah, 4 derivatives seems like a lot, but it's not so bad in this case. A lot of terms you're going to be able to notice are zeroing out. So let's look at the first derivative. This is the e to the 1/2 t squared times the derivative of what's inside, which is 2 times 1/2 times t. So we just get a t. And you can see when you plug in t equals 0, that this is 1 and this is 0. So we do get that the mean of the standard normal is 0. So we're on the right track. The second derivative is going to need a product rule. So I get the first times the derivative of the second. Now the derivative of this part is going to give me the t again out front. So I'm going to go ahead and put that there as a squared and just write the rest out. plus the second term times the derivative of the first term, the derivative of the t, which gives you 1. And if we plugged in t equals 0, this first term is going to disappear, and the second term, e to the 0, is going to be 1. And we do know that the expected value of z squared is 1, so we're still doing okay here. Let's go to the third derivative. I'm going to use the product rule on the first term, which will give me the first term t squared times the derivative of this, which is going to give me the e again, but it's going to pull out another t, so I'll end up with t cubed. And then I'll get the second term, which is the e part, times the derivative of the first. The derivative of this part is 2t. And then the derivative of this final term. So this, again, is not hard to evaluate because of this t cubed, this t, and this t. When I plug in t equals 0, I get 0. So here is us showing that the expected value of z cubed is 0, which before I just tried to argue with symmetry. We're so close. One more derivative. Can I use 4 primes, or do I have to go to the... I'm going to use 4 primes. Product rule here, I get t to the 4th e 1/2 t squared plus 3t squared e 1/2 t squared. I'm now going to move into this term, product rule that. And finally, I'm going to product rule this last guy over here. Again, there's a lot of leading t's, so a lot of these terms are going to zero out. The expected value of z to the 4th is the 4th derivative of the moment generating function evaluated at 0. So this term is going to zero out, this is going to zero out, this one is going to go away, this one's going to go away. We're left with this and this. And each of those e's are e to the 0, which is 1. So I end up with 2 plus 1. Again, that's this coefficient and this coefficient, or 3. Let's finish this off. This is kind of a long one, and I did it the long way. I'm going to do the chi-squared approach next, and it's going to be a lot quicker. We wanted the variance of our umvu. We noted that adding or subtracting a constant does not affect the spread of what we're looking at, so we can drop that. And then we rewrote this as this big mess. We observed already that the expected value of z squared is 1. So this is 1, this is 1, and this is 3. And so I've got 3 over n squared plus 4 theta squared over n minus 1 over n squared. So I have 4 theta squared over n plus 2 over n squared. And that is the answer to part B, the variance we were trying to find. So what about that chi-squared hint? I would still approach most of this problem the same way, but you can use the chi-squared hint to avoid looking at those moment generating functions. The expected value of z to the 4th is the expected value of z squared squared, and a standard normal squared has a chi-squared 1 distribution. So this is the same thing as the expected value of another random variable, say w squared, where w has the chi-squared 1 distribution. And we can find the expected value of w squared by looking at the variance of w plus the expected value of w all squared. And you're even given the variance and expectation for the chi-squared. The variance is 2 times the degrees of freedom, so 2 times 1 in this case. And the expected value is the degrees of freedom, so 1 squared. And we get 3 again. And that was certainly a lot easier. So maybe we should have followed the hint, but I imagine that I don't know, that if you don't see how to use it, you're going to try different methods, and maybe moment generating functions will be the way to go. So in the end, you will get the same variance, the same answer for part B. Okay, in part C, we want to figure out whether or not our estimator is efficient. So let's recall the variance. And an efficient estimator is one whose variance achieves or equals the Cramer-Rao lower bound. An inefficient estimator has a variance that is larger than the Cramer-Rao lower bound. The Cramer-Rao lower bound is a lower bound on the variance of all possible unbiased estimators of something. So you really shouldn't be using it to talk about something that is biased. But if you do, if you have a biased estimator, its variance could potentially get below the Cramer-Rao lower bound, and we would call that a super efficient estimator. In any event, we need the Cramer-Rao lower bound for estimating theta squared. This Cramer-Rao lower bound is equal to the derivative of our function that I'm calling tau of theta squared over the n-dimensional Fisher information. And in the IID case, the n-dimensional Fisher information is n times the one-dimensional Fisher information. To find the one-dimensional Fisher information, I am going to need the PDF. Do you have to move to one dimension? No, you can use the joint PDF and go straight for the n-dimensional Fisher information. This is e to the minus 1/2 x minus theta squared. We want to look at the log of this. So I've got 2 pi to the minus 1/2, and that'll give me minus 1/2 log of 2 pi. And then this product up here plus the log of this term, which will be minus 1/2 x minus theta squared. Next up, for going for the one-dimensional Fisher information, is to look at the partial derivative with respect to theta. So there's no theta in the first term, and the second term I'll bring down the 2 and do a little chain rule, and we will end up with positive x minus theta. Okay, so one way to find the Fisher information is to square this, put the capital X in, and take the expectation. And you can manipulate that to, you don't have to manipulate that. That's the variance. So I probably wouldn't do this, but in case anyone is going this way, the one-dimensional Fisher information is the expected value of this derivative with a capital X1 plugged in, and that whole thing squared. And this is the expected value of capital X1 minus theta squared. And because theta is the mean for X1, this is the variance for X1, and that was 1. But the other way to do this is to go to the second derivative. So if I look at the second derivative, or the derivative of that derivative there, I'm going to take the derivative of this with respect to theta. The x part is 0, and the other part is 1. And we do have another form for Fisher information. It is the negative expected second derivative. And that's going to give us positive 1. Oops. And that's going to give us positive 1 again, which is a good thing. So we've got our Cramer-Rao lower bound. Remember, we're trying to estimate tau of theta equals theta squared. The Cramer-Rao lower bound for theta squared, or for tau of theta, it's going to be the derivative over the n-dimensional Fisher information. In the IID case, the n-dimensional Fisher information can be simplified a little bit into n times the one-dimensional Fisher information, which we just found. The derivative of theta squared with respect to theta is 2 theta, and then that all gets squared. And then n times 1 down here So we get 4 theta squared over n. Remember, the variance of our estimator was 4 theta squared over n plus 2 over n squared. So this is strictly greater than, for all integers n is a sample size, positive integers, 1, 2, 3 on up. It's strictly greater than the Cramer-Rao lower bound for theta squared. So the answer is no. The estimator is not efficient for estimating theta squared. Okay, in the next part, part D, we want to find the maximum likelihood estimator, and then we're asked for bias and variance. And it seems like this problem is getting really long, but I think we've done most of the work for that bias and variance. So let's look for the MLE. Here's where we need to write down the joint PDF. I'm not going to start with the one-dimensional PDF because we've done this a few times now. So the joint PDF is 2 pi to the minus n over 2 and e to the minus 1/2 sum of the xi minus theta squared. And so for a likelihood, I am going to drop this. I can square this out and drop the first term after running the sum through because that's the x's only, but I'm too lazy to do that. So let me just take the likelihood to be that e part. Again, if I squared it out and ran the sum through, then there's more constants of proportionality to be dropped. I'm going to look at the log of the likelihood, which almost always makes maximizing the likelihood easier, but sometimes it doesn't. And so remember, your goal is not to take the log. Your goal is to maximize the likelihood. And if taking the log made things worse, then don't take the log. But definitely here, because we have an e, it makes things nicer. I'm going to take the derivative with respect to theta. I'm going to take that derivative through the sum and pass the negative 1/2. Bring down the 2, xi minus theta, multiply by the derivative of the inside, and I get some cancellation here. I get the sum of the xi minus theta, and I can run the sum through and get the sum of the xi minus n theta, and then set that equal to 0. And then solve for theta, make things capital, and put a hat on it. And you have your MLE, which is x bar. Here, you can easily see the second derivative with respect to theta. This part is 0, and you get negative n. So it is a negative second derivative, which means that we did find a maximum and not a minimum. What we've written is the MLE for theta, and I want the MLE for theta squared. So let me put a little MLE under here. And we want the MLE for theta squared. So the MLE is an invariant estimator. And that means that you can take this function and plug your MLE in. That is the invariance property of MLEs. So the MLE estimator of the theta squared is going to be x bar squared. Now let's look at the bias and the variance. The bias of the MLE, this is the bias of x bar squared, and the bias is defined to be the expected value of x bar squared minus the thing you're trying to estimate. So if you have an unbiased estimator, this will equal this, and you'll get a bias of 0. I already know what the expected value of x bar squared is. I don't want to scroll back up, and I don't want to have to go through any computations again. Note that this is the expected value of x bar squared minus 1 over n plus 1 over n minus theta squared. And this thing is an unbiased estimator for theta squared. So this is the expected value of x bar squared minus 1 over n plus 1 over n minus theta squared. And this from part A, we know that the thing in the expectation is unbiased for theta squared. So we get a bias of 1 over n. Let's find the variance. The variance for the MLE, this is the variance for x bar squared. So this is something we've already computed because this is the variance for x bar squared minus 1 over n, because it doesn't matter if I add or subtract a constant. And that is the estimator from part A, and we found its variance in part B. This is 4 theta squared over n plus 2 over n squared. Same variance as before. In the final part of this problem, we want to look at the mean squared error of the estimators. And it does give a nice hint relating the mean squared error to the bias and the variance. So let's do it. The mean squared error for the UMVU that we found in part A, because that's an unbiased estimator, the mean squared error is the same thing as the variance. And we know this variance to be 4 theta squared over n plus 2 over n squared. The MSE for the MLE, this is not the variance of the MLE because there is some bias. If you took MathStat with me, we showed that the variance is the MSE minus the bias squared. So that means the MSE is the bias squared plus the variance, which is given to you in the hint. So we know this. The bias we computed was 1 over n. And the variance is the same thing as the variance in the previous part. So we get 4 theta squared over n plus 3 over n squared. So the MSE for the MLE is actually greater than the MSE for the UMVU, which it's certainly not going to be lower, but they could possibly have been the same. I mean, the UMVU has the lowest variance. Actually, it could be lower because the MSE is not unbiased. So it's not going to have, the UMVU is only the lowest variance for all unbiased estimators. And if the MLE is biased, then its variance could, in theory, be lower than the variance of the UMVU. So this concludes August 2018, problem 4.